Hello everyone and welcome to this lecture. In the past lecture we just defined what is a contour integral and we try to give some motivation for it, and in this lecture we are going to see some detailed calculation on how we can evaluate contour integrals, and we will also learn that to do some contour integrals you need to do some parameterization, because remember, contours can be parameterized if you recall your lecture from what is a contour and all that. So the best way to learn about this integral is through some examples. So we are going to consider an example. Let's call it example 1, and we are going to consider a function f of z which is z bar, and remember that z is just x plus iy. It's just a complex number and your function is z bar. That means z bar would be x minus iy, and we'll see how the idea of parameterization is inherited to this evaluation of these contour integrals. So I have given you the function. Now we need a contour. That is, we want to evaluate this guy over here, f of z dz over some contour c. And for this example we are going to choose a contour in the complex plane. Let me draw the complex plane first. I am drawing with some dashed line, or you can just draw it with some solid line as well. So let me use a different color to denote some contour, and this is one contour. This should be a straight line over here, and let's call this is the origin, that is the 0, 0 point, and let's say this is 1, 0, and this point over here is just 1, 1, and this is a contour. Let's call this contour as c1. That means if we label the points as A, B and C, then our contour C1 will consist of two lines, and you can see that these are piecewise smooth curves on this complex plane, and you can always label them as real axis and imaginary axis so that you don't get confused. And this C1 will consist of AB and BC, right? Don't take this plus as a literal meaning of addition. It just means that these two pieces make up our contour. So how do we go about evaluating this guy over here? That's the thing we are going to learn now. So one fact about contour integrals is that since these are piecewise smooth curves, what you can do is that you can break down this integral into two parts. That is, one coming from AB, another coming from BC. So let's do that first, and obviously we are going to substitute f of z equals to z bar, that is given over here in the first line. So at first we are going to evaluate this integral on the line AB, and you have your z bar and dz over here, and then you will have BC, z bar, dz, right? Okay, so z bar was x minus iy and z was x plus iy, right? But you now have to go to xy, that is, instead of integrating over z's, you need to decouple them, because you can see that these contours are an example, that is this AB and BC. These two lines are example of constant parameterization, because on AB there is no variation in y, so y is fixed over there, and on BC there is no variation of x, that is x is not changing. So since you have written z is equals to x plus iy, you can easily find dz by using your theorems on calculus that you learned in high school, or let's say your preliminary calculus courses, that this dz is just dx plus I dy, right? So what is this z bar dz? That is the thing we want to evaluate right now. So let's try to evaluate z bar dz. So this will be x minus iy times dx plus I dy. Now you just do the algebra to find out these expressions that is appearing over both of these integrals, that is the integral evaluated along path AB and along path BC. So this will be x dx plus I x dy, then there will be minus iy dx, and then there will be minus I squared y dy, and minus I square is just plus 1, that is I squared is equals to minus 1, and this minus and minus will cancel out and it will give a plus. So finally you will have x dx plus y dy, and then you will have I x dy minus y, there will be I over here, and dx. This is our z bar dz, right? And now since we have reduced the expression from z to x and y, now we can easily find the limits of x and y, and we can use that to our advantage to evaluate this integral over here. So let's try to do that. So first what we want to do, we want to evaluate this part. Let me just highlight it. This is the thing that we're going to evaluate first, and this is the thing that we're going to evaluate second, and then we'll add them, and this will give us the final result, that is the integral of f of z over this whole contour. Obviously there should be a c1, that means from A B C, like this, and you will see that this result is actually path dependent, because we'll take another contour from A to C and we'll see that it depends on the path. So without further ado, let's try to evaluate it in AB. So this part is just AB of z bar dz is equals to this thing. So let's write it down, x dx plus y dy. Obviously this integration is a linear operator and it will just hop into all of this expression that is in front of them, and then you will have x dy minus iy dx. So along AB you can note that your x is varying but your y is not varying, right? So y is a constant, and that y constant is 0. Along AB y is 0, and that means dy is also 0, and your x is changing from 0 to 1, right? So the lower limit will be 0 and the upper limit will be 1. So x low, let's say 0, x up, that means the upper limit is 1. Now using all this information we can evaluate this guy over here. So let's try to do that. In this integration, since y is 0, you have to put y equals to 0 over here. So now you can see how this parameterization thing is working for contours, because you can see that you are parameterizing y as 0 and dy also 0, but x is changing. So now you need to put these parameterizations in the above expression over here and evaluate this integral. So if you do that, this will be 0 to 1 because x is changing, and this x dx term will be there. Y is 0, so this part won't be here, and dy is also 0, so this part won't be here. And then again this part over here, it contains another y, but y is 0, so this part won't be here as well. So this x dx will just give you an x square by 2, 1 to 0. This will be just 1/2, right? So yes, there is x dx, and this will be x square by 2, 1 and 0. This is just 1/2. So this is for part AB. What about BC? You can see that for BC, so let me just write it down over here, and obviously I'm gonna draw this whole thing again so that it's kind of easier for you to visualize what's going on. Again, this is A, B, C, and this was 0, 0, 1, 0, 1, 1. And along BC, your x is equals to 1. So along BC, x is equals to 1. That means dx equals to 0, and y is changing, and the lower limit of y, that is the y low thing, is just 0, and y up is just 1, right? So similarly, like before, you have to write this whole thing down. So let's do it. This will be BC, and you'll have your x dx. I'm gonna write the full thing down, and then I'm gonna use these parameterizations to simplify this expression. Y dy plus ix dy minus iy dx. Since x equals to 1, there will be x equals to 1 everywhere in this expression. However, you can see that the dx is 0. So due to that, this part will go away. That means it won't contribute, and this part will go away. And now, since this two part goes away, however this part remains, and you can see x equals to 1 along BC, so you have to put x equals to 1 right now, and in this integration you have to put the limits of y, because in this contour, that is along BC, only y is varying. So again, this is just 0 to 1, because y low is 0, y up is 1, and you have y dy, and then you have 0 to 1, x equals to 1. You can pull back this I outside this integration because it's a constant, imaginary number, and you will have this dy. So this is pretty easy to do. This will just be 1/2, because this part will give you a y square by 2, and there will be limit of 1 to 0, so this is just 1/2 plus 1 to 0. If you integrate dy, this will be just y, and there is I over here. I times 1 is just 1. Note that I'm not writing the integration constants, because when you add all the constants up, it becomes another constant. So that's why I'm not doing that. And obviously this is a definite integration, so there is no room for that as well. So this is 1/2 plus I, right? Okay. Now what we need to do? We need to just, let's say this is 1, that is the integral along path AB, and this is in equation 2, and we just need to do 1 plus 2. So 1 plus 2 should give us this thing, right? AB of z bar dz plus BC of z bar dz, and if you add them, that is add these results, 1/2 plus I and 1/2, this will just be 1 plus I, and this is the exact result for this contour, that is f of z dz. So this is our result. This is one way to calculate this integral. Now what we're going to do is that we're going to see that this is this result that we just got from evaluating this contour integral is actually path dependent. So let me highlight that out. So these contour integrals are in general path dependent. However, if your function is an analytic function, it's not going to depend on the path, but we'll see more of that later. For now, let's accept this, because these are similar to line integrals, and line integrals depend on the path you select to traverse on. So now we are going to choose another contour from 0 to 1 1, but this time instead of using the path over here, we are going to choose another path from A to C directly, and this is parameterized by, that is, this green line is parameterized by y equals to mx plus c, where the value of m and c you can get from this 0 0 and 1 1 point, and I'll show that how you can do that. This is something you learned from coordinate geometry, and we're going to evaluate the same integral, but this time along this green line. So again, let me draw this whole thing again. This is A, this is C, and this was these red lines were the first contour, sorry, it was the first contour that we used for the evaluation of this integral. So this is our B. Again, let's write the coordinates down, 0 0 1 0 and 1 1, and let's call this green line as the second contour, C2, because we denoted the first contour, that is denoted with this red line, as C1. And now what we ask is that we want to evaluate this integral f of z dz, that means z bar dz along the second contour. However, now you can see that x and y are related somehow, and since this is a straight line, that is C2 is a straight line, and in this straight line x and y are related with each other through the equation y equals to mx plus c. Now this c is the constant that can be determined from these points 0 0 and 1 1, and this m is just the slope, and from these 2 points, that is 0 0 and 1 1, you can see that c is 0 and m is equals to 1. So the parameterization, that is the dependence of y and x with each other, is denoted by y equals to x, right? And from this relation you can easily deduce that dy equals to dx, right? So you see that along this line, that is the green line over here, x and y, both of them are varying. So naturally you would expect that you should get a two-dimensional integral, but because of this relation over here, that is the parameterization, you are getting a single dimensional integral, and that will be evident when I write the whole thing down. So again, I'm going to write this whole thing down along AC. Z bar dz is that AC, and if you recall from a few minutes ago, what was z bar dz? This was the thing, that z bar dz. So let's write that down. It was x dx plus y dy plus I x dy minus I y dx, right? But you already have these two relations over here to simplify your expression over in this integration, inside this integral sign, that is y equals to x and dy equals to dx. So let's just put them over here. So you can see that I'm not writing the limits right now, I'll write them in a few minutes. So x and y, they're equal, so I just want to replace all the y's I want to get rid of y's and I just want this function, this integral in terms of x. So I'll keep the x, and instead of y I'll just write x, instead of dy I'll write dx, and so on. So if you do that, this will just be this, right? Now this is a pretty neat relation. You can see that these two terms cancels out, and all you have is just 2 along this path AC and x dx, right? Now since this is an integration on x only, you just need to find out the lower limit of x and upper limit of x along this green line. So the lowest value, that is the starting point, is 0 because you are going like this. Let me just highlight this again. You are going like this, right, from A to C. That's the crucial part, that is you are going from A to C. That's why you are saying this AC thing. If you went from C to A, you would have write CA. So we are not considering CA and we are considering AC. So this direction is also important when you do contour integrations, and this direction is sometimes called orientation of the contour. So as I was saying, that our integration was 2 times x dx, and all we need to do is to find the lower limit and the upper limit, that is the starting point and the ending point. The starting point is 0 and the ending point is 1. So let's just put them over here right now. Two 0 to 1 x dx, and this is just x square by 2. There will be a 2 over here. These 2 will cancel each other out. There is 1 and 0, and this is just 1. So the contour integral of that function, that is the z bar dz or f of z dz, whichever way you want to call it. You can write C2 to denote AC, or you can just directly write AC, it doesn't matter. Now you can see that its value is 1. So let me just summarize the result for this video. Summary: when you evaluated z bar dz along AB plus BC, that was C1, the contour over here that is denoted by this red line. Okay, let me just in fact switch the color so that you can understand what is happening. So along C1, that was denoted by AB plus BC, you had this C1 z bar dz as 1 plus I, right? That was the result we got. And along the green line, that is denoted by C2, that directly went from A to C, you had C2 denoted by this. You evaluated the same integral, but now the result is 1. So we conclude that contour integrals are indeed path dependent. That means they are contour dependent. Whichever contour that you are choosing, also the orientation. And this is a very simple example of how to evaluate these contour integrals. That is, first, it totally depends on the situation, because you can see that there is no complicated relation between x and y. That's why we got very lucky by doing all this. But in the next video we are going to see that there might be some other parameter that is not in the complex plane, but it's running in the background or something like that, and using those parameterizations and using the polar form of complex numbers, we are going to solve some complex contour integrals. So it will totally depend on the problem, and most of the time the parameterization will be given to you. And this will be it for today, and I'll see you guys on the next lecture. Thank you.